Hello everyone. Today we're gonna explain electricity, electromagnetic induction, and self-induction. So first of all, we start with the electromagnetic induction. What is electromagnetic induction? It is the process of generating an electromotive force or voltage in a conductor when it is exposed to changing magnetic field. What does this mean? It means by moving a magnet next to a certain coil, we generate electricity. That's called electromagnetic induction. So, magnet plus coil, it results in electricity. So we generate current. Okay. So the motion of a magnet, so whenever we place the magnet near the coil, we generate a magnetic field, which then induces current. And there's something called magnetic flux. What's magnetic flux? There's a difference between it and magnetic field, but of course it's related. Magnetic flux, it's the total amount of magnetic field passing through a given surface. So, magnetic flux can be in a circular surface or it can be in a solenoid or a coil. And each one has its own formula. So first of all, if it was in a circular or a loop, it can be, so first of all, we have a normal vector, okay? This normal vector, of course, it's always perpendicular. And the magnetic flux, it's either opposite to the normal vector or it's parallel to the normal vector, okay? And the rule for the magnetic flux, it's this one. When do we use it? We use it when we're talking about a circular surface or a loop, okay? And this theta, it's the angle between the magnetic field and the normal vector, okay? So, here, we want to know this angle, okay? So, whenever they say that the magnetic field is opposite to the normal vector of the loop, this means that the angle between them is 180 degrees. Or they can say that the magnetic field is inwards, but the normal vector is outwards. So when we have opposite positions, okay? When one's outward and one's inward. So, and when is it 90 degrees? When the magnetic field is parallel to the plane, okay? So the field is perpendicular to the normal vector. Or they might say that the magnetic field is inwards and the normal vector is also inwards. So the angle between them is 90 degrees. And for a solenoid or a coil, there's another formula where we add to it number of coils, okay? Since the current is being generated and is passing through these coils, okay? So in this case, we have to know the number of turns in a coil. And we want to pay attention to the unit, that the influx, its SI unit is Weber, while the magnetic field, it's Tesla. And we have the surface area, which is always in meters squared, okay? For example, a circular loop of radius equals 10 centimeters is placed in a uniform magnetic field of magnitude B equals 0.1 Tesla for an arbitrary chosen in a positive direction, okay? Calculate the magnetic flux crossing the loop if its place makes an angle 30 degrees with beta, with B, which is the magnetic field, okay? So, first of all, we draw the normal vector. Deal? Okay. Then, we draw a line. And here's a circle. they told us, okay, they told us that B, or the magnetic field, it's in the positive direction. What does this mean? So here, as if we're taking the positive from here, so we draw an angle which is 30 degrees. And this angle which is 30 degrees, it's the magnetic field. Okay? And the total angle here, since that's the normal, it's 90 degrees. Then, what's the angle between B, which is the magnetic field, and N, which is the normal vector? So in this case, and N can also be called A, okay, not to confuse yourself. Okay, so what's the angle between them? It's 90 minus 30, which is equals to 60, okay? So that's how we calculate it. And what we have given is that we have the R, which is the radius, then it's given, okay? And we calculate the surface area, which is pi r squared. That's the area for a circular loop. Okay. Example 2. A solenoid of 1000 turns, each of surface area 30 centimeters squared, is placed in a uniform magnetic field of magnitude B equals 0.2 times 10 to the power minus 4 Tesla. The solenoid is held so that its axis is parallel to B. Okay, we want to pay attention to the word parallel. Okay. Now here, we have to know the sign, it's not very important because it depends on the question. Okay? And first of all, we want to calculate the magnetic flux to the solenoid where the positive direction is anti-clockwise. So we consider that the positive direction, it's anti-clockwise. And the normal is always outward. Okay? And beta here, it's inward because they told us that the positive direction, it is anti-clockwise. So in this case, the angle is 180 degrees because the normal is going outwards while the magnetic field, it's going inwards. Okay? And we apply the formula. But if they needed the answer in positive, okay, then we consider that the magnetic field is going in the other direction, so it's parallel with B. Okay, so it's cosine 0. And in this case here, they told us that it is parallel to B. Okay, so the cosine here, the angle between them is 0. So we're gonna have a positive answer. Okay, so when the direction of the normal vector and the direction of the magnetic field are opposite to each other, we have a negative answer because cosine 180 is equals to minus 1. While if they are both in the same direction, then cosine 0, because here the angle between them is 0, so it's gonna be equals to 1, so it's positive. So it is 90 degrees when N is perpendicular to B or when B is parallel to the surface. It is 0 degrees when N is parallel to B and they have the same sense. It is 180 degrees when N is parallel to B and having opposite sense. Okay? Here we'll talk about the variation of the magnetic flux. Okay, so what do we mean by the variation of the magnetic flux? Meaning the change in the magnetic flux. So, first of all, there's a rule by Faraday's law that states the change in the magnetic flux. The magnitude of the induced electromotive force in a coil is directly proportional to the rate of the change in the magnetic flux. When we say rate of change, we mean that we have to derive it. Okay, so first of all, we knew that E equals to N d of the magnetic flux over tt. Okay, so why did we add the negative sign?